So
Yeah,
imagine you're in the Millennium Falcon and you're flying into this small dinosaur bone.
that's no moon.
It's no bigger than this. Dinosaurs are awesome, and I really uh, I want to know how they were awesome. Dinosaur nerd in me is just saying, Tyrannosaurus was good at whatever it did at every age. We're looking about how the dinosaurs were awesome. Like, I don't care if T-Rex could run 50 miles an hour or 12. If it's running 12, that's scary. Kyle calculated something pretty terrifying for an adult T-Rex.
Dr. Snively has been an incredible, prolific user of technology. You can see behind me screenshots, histology. You've got finite element analyses. You have CT scans, synchrotrons, uh, the ankle paper that came out recently, anatomy, technology, dinosaurs. I mean, what's more to love? This is fantastic. So, Dr. Snively, thanks for your work from the '07 paper and probably some others I've referenced over the years, but that one has just kept coming back for musculature and anatomy.
Thanks to them, we're learning a hell of a lot about how carnivorous dinosaurs really operated. Lots of neat stuff still to come on dinosaur feeding.
That was amazing. The chat is just replete with all kinds of questions.
A quick note before we continue. This conversation with Dr. Eric Snively only gets better as we go, and the audience Q&A later in the episode is especially worth staying for. If you want more real paleontological conversations like this, subscribe to the Fossil Crates YouTube channel. That support helps us bring on more great guests, and these episodes keep coming. Let me know in the comments who I should interview next.
Hello, everyone. It is high noon in Phoenix, Arizona. I'm finally back home after this 6-week whirlwind roller coaster road trip we've been on. I just got back from the International Association of Amusement Parks, and what a crazy experience that was. We'll save that till the December wrap up, though. I'm going to include some info in that. But today we have an absolutely special guest, and I am still smiling from having Dr. Eric Snively with us today. Dr. Snively has been an incredible, prolific user of technology. You can see behind me screenshots, histology. You've got finite element analyses. You have CT scans, synchrotrons, the ankle paper that came out recently, anatomy, technology, dinosaurs. I mean, what's more to love? This is fantastic. So, Dr. Snively, thanks for your work from the '07 paper and probably some others I've referenced over the years, but that one has just kept coming back for musculature and anatomy. But can you tell us, talk to us about yourself and what you're up to and how you got into paleo?
Hi, Brian. Thanks very much. And hi, everyone. Uh, so I kind of got into paleo from a really early age. So uh, uh, my dad was stationed in Utah, and I was in a barbershop, and there was like a dinosaur footprint in this barbershop in Ogden, Utah, or a cast of a dinosaur footprint. I kind of got uh, started bugging my parents about dinosaurs then, and I haven't really matured since. So that's really how I got into it. And then I had a fairly traditional route. I went to University of California, Berkeley, worked there with Kevin Padian and my mentor, Jessica Theodore. She was a grad student at the time, and some other folks I still know, like Greg Erickson and Ann Weil and John Hutchinson, were all grad students at the time. And I've really maintained contact with them, sort of through research and inspiration and everything else. And so I went to the University of Calgary up in Alberta to work with Tony Russell, and got master's and PhD there. I went up there to work with Tony, and it had the big advantage of the Royal Tyrrell Museum there and the chance to do field work in Dinosaur Provincial Park, and to work with Phil Curry. And I went on to do a postdoc with Phil and with Eva Koppelhuis at University of Alberta. And subsequently, I got I realized I could get an engineering degree, and I could learn the things I was kind of figuring out on my own. So I went to Ohio University to work with John Cotton, who's a great expert in engineering mechanics, and I kind of did a postdoc there with Larry Whitmer, and I started a great relationship there with Pat O'Connor, who's both Larry and Pat have been on Paleoportal, and I taught comparative anatomy for 6 years at the University of Wisconsin-La Crosse. And while I was at Ohio, I helped out some grad students, and one of them had gotten a job at Oklahoma State University, and that was Haley O'Brien. I'm forever grateful to her for recruiting me like crazy for my current position. So that's pretty much the story.
That is so fantastic. It's funny you mentioned John Hutchinson. I met John way back in '95.
Wow.
And maybe even '94. My first SVP was Albuquerque in '94, '93. Anyway, I've known John. He was a guest here as well. So we've talked to John about his take on Tyrannosaur motion. And Dr. Lopez went to Berkeley.
All right. Oh yeah.
But yeah, we got Berkeley.
Yay, Berkeley.
Yeah.
So it's such a small world we live in the realm of paleontology. You're 2 emails away from just about anyone on the planet.
Yeah, that's absolutely true.
Now, do you have an actual degree? I mean, you went back and got an engineering degree as well?
Yeah, so I have a Master of Science in biomedical engineering from John Cotton, again at Ohio University, and I found that as I was sort of starting out for my PhD, I was, rederiving mechanics that people had figured out hundreds of years ago, and I'm not that bright. So that I realized that wait a minute, I could just go to classes and learn these things, and so I was able to join John's lab, and that's where I did some work on Allosaurus neck motion and on dinosaur agility that's sort of continued on since then.
That is so awesome and amazing. And you are taking graduate students. You have an active lab.
Yeah, I'm pretty topped up for the moment, but yeah, I have Kyle Atkins Weltman, who spoke with you guys, and Kyle is doing just amazing stuff with large scale ecosystem interactions, sort of melding them with biomechanics. And Kyle's a wonderful digital sculptor, and so yeah, he's figured out some really cool things about dinosaur turning ability, and so Kyle's going to town on that. Kyle and Evan and I are collaborating on Veranid lizards and how they feed. So Kyle is and active in reptile husbandry. So he keeps Veranid lizards and snakes and turtles. So that's Kyle. And then Andy Dannison, he is now redescribing the material of Saurophaganax. And I'd like to get him in touch with Colin Boisvert about all that. And Andy's also going to be doing biomechanics of arms of carnivorous dinosaurs. So that ties together well. And my student, Brenna Hart-Farah, and we're going to see a lot of her work today. She's doing synchrotron 3D imaging, and she's basically turning the world of, let's say, the world of histology upside down. She's turning it inside out and expanding it. So Brenna is showing us what we see in thin sections, what those things are actually doing in 3 dimensions. And Holly Woodward Ballard, she's Brenna's co-advisor, is one of the top histologists on the planet, one of the top dinosaur experts. And so Brenna is, Holly realized that like Brenna can do the 2D histology, but I can lead her on the sort of the synchrotron micro CT 3D histology. And Brenna's just shot past whatever we can do. My last grad student is Amanda Pennings, and we'll see a little bit of her in my presentation. And she did a really awesome poster on the Gorgonopsid Inostrancevia, which is a giant fang-toothed mammal relative. And Amanda is really interested in variables. So how you can tell whether you're getting the right muscle force, how you can tell if you're getting the right stiffness of bone. And Amanda is sort of, she's exploding onto the scene with racehorses. So racehorses are going to be, quarter horses and thoroughbreds are going to be a big focus of her bringing together histology, biomechanics, muscle, and how we can, it's sort of in the manner that John Hutchinson has really shown us how to do. Amanda's going to show us what our variables really mean. So what the spread is, what the effects of variables really are, how certain ones are more important than others, and how we can test those variables using mechanical load testing, using other kinds of extant methods. So those are my four current grad students. Evan Johnson Ransom is a former grad student. Andre Rowe is also a former grad student. Andre's been doing stunning work over in the UK with Emily Rayfield, and he's now Dr. Andre Rowe. And Andre has also sort of went the Tyrannosaur route a bit like Evan did. Both of them have expanded out into other theropods. And thanks to them, we're learning a hell of a lot about how carnivorous dinosaurs really operated.
That is an amazing portfolio and quite the roster of troops in your stable, current and former. Kyle and Evan have both been on Paleoportals as speakers and presented. Please, if you don't mind, introduce me to Dennison. I was up there a couple days ago with Christy. We were looking at snacks material again, and I've taken on an unhealthy interest in it because I have two skeletons in my backyard that are traits. So I'm trying to figure this out. I have a cast of behind me. I've got you can't see it, but I have the cast of the big femur. And so I've been poking around, and Jacqueline wanted me to meet him, but when we were in town, we didn't get a chance to. So if you don't mind making that connection as well, I'd love to, any kind of resource I can be to him, sign me up. I'd love to help in terms of providing whatever I can. Giggle factor, if nothing else.
Well, that's terrific. And Andy's discovering some very intriguing things about the material, and he's going to be doing what he can on biomechanics of forelimbs and sort of scaling what we can get from Saurophaganax, just reconstructing what we can of that. That's going to be really fun as well. So Andy would be really, he'd be really enthralled to talk with you, I think. About
I'd have a ball. And you mentioned Veranid, so I will take a moment to share something that just happened. That no harm, no foul. Everything was okay, but it's so amazing how fast the world can change potentially. So we're at a place called Golf and Gators over a couple nights ago in Florida, in Cocoa Beach. And they have wild animal interactions. And we were working with Safari Todd and Jungle Jen. And these are professionals. They've been doing this 30 years, thank goodness, in hindsight. And they asked if I wanted to handle and play with and photograph an Asian water monitor. And I said, sure, why not? And so I've been handling snakes, and one of them had vented on me. I mean, there was a lot of tongue flicking. Everything was really interested in me. And so none of us put what I had done earlier in today, which was hang out in a dermestid beetle colony lab, together until the monitor was named Smog kept poking his head in my pockets, trying to go up my shirt. So he climbed around my back, and Christy's behind me to my right, Todd's to my left, and I see Jen in front of me. Jen's face gets really terrified. I hear Christy gasp, and I see a motion like a really fast hand. Turns out Smog wanted to take a bite out of me to see what I was made of because I smelled so much.
Oh, wow.
it came within probably a millimeter or two of having a really bad night with the water monitor biting me right in the back of my neck in a really sensitive, highly vulnerable spot, just because it was so curious as to what it was tasting. And it was tasting dead mammals' flesh that had been wafting all over me for an hour or so. So when you mentioned Kyle and monitors, I got a little shudder. I had to share the dangers of with live wild animals, or semi-wild. So,
Yeah, it was scary.
I digress. I took it a lot better, I think, than Christy did, because she realized she'd had to have driven home in the rainstorm with me all bleeding.
Well, yeah, you couldn't see it because he was behind your neck, but I saw it as his mouth started to open, and thank God that guy grabbed his jaws. So,
Wow.
Lesson learned. But I commend all of you for playing with those Veranids. These are some the Salvadori, the teeth on those things.
Yeah,
Right?
yeah.
Ray Wilhite's got one in his lab, and it's just incredible. The skull, not a living one, but. And then you mentioned one of the animals that has always made me smile, which is I don't know how to say it. You said Inostransevia or
Inostransevia?
Inostransevia. Good. I'll change my pronunciation.
I don't know if that's right or not. But that's how I say
well,
it.
I'll move it around. I'll workshop it with people, see what I get. But we have one of those here at the Arizona Museum of Natural History, and we have a cast of it. And so I get to go by and look at it and see its dentition. And I mean, it's a cast, but it's still so cool to see such a crazy, neat beast. And now to know someone's looking at this in earnest, I'm going to 2 thumbs up that research. I can't wait.
Yeah, we'll see what Amanda can do with it from now on.
If there's anything I can do there, I mean, she obviously has cast, or if she doesn't, if she needs some, come on down. We'll let her play with it.
Oh, that'd be awesome. Yes, thank you.
Cool. So you've got screen share because you mentioned you might have a presentation for us.
I do, and I'm kind of terrible with Zoom getting so they're sharing the right screen. So we'll see if we can do a presentation view of PowerPoint. So I'm going to share my desktop over here, and
perfect.
And let's see if this presentation here works. So you guys can probably see that. Can you see your images as well, or should I drag those down?
Oh no, we see your screen and it's
just the background. Okay, well that's good. So
OSU, yeah, osteopathic medicine and nothing else.
At the Cherokee Nation, good. So, so it's really neat, like watching Paleo Portals talks and how everyone sort of comes at paleontology from different angles. And Pat O'Connor is very interested in very large questions and sort of what you can, what animals you can use to answer those questions. And I have a much more sort of childish motivation. It's it's no bigger than this. Dinosaurs are awesome, and I really I want to know how they were awesome or not. And so that's sort of how I approach paleontology. And to do so, you have to stop sort of at every step along the way. So so I study birds a lot. So I've done a lot of work with extant birds, with extant raptors, a lot of dissections of birds and other modern reptiles, and sort of working physically with them, both using physiological experiments and then with the raptors themselves, doing sort of high-speed video of how they operate, and that gives me insights into like what T-Rex might have been doing. And by reconstructing, say, the muscles of living animals, I'll give a shout out to Brian here. So this is my favorite room on the planet. This is the Museum for Naturkunde in Berlin with the Giraffatitan, Diplodocus, and Dicryosaurus. And you can use extant birds to sort of reconstruct things like neck musculature, just larger scale elements of the neck, based in part on what we can learn from birds. And of course, sauropods have their own wonderful peculiarities and size. And so it's funny when like I'm very much into theropods, but when I put them uh, next to the say the cervical vertebrae of a sauropod, the theropods are kind of uh, they're trying, but they're just not quite there. And so a lot of the stuff I've done has been like reconstruction of neck muscles and motions and the physics of neck motions in carnivorous dinosaurs. So here's a Tyrannosaurus rex, and from an older paper, Allosaurus from slightly more recent paper. And we sort of continued with these studies. Andy Dannison has actually done some work with in collaboration with Oliver Damuth and Heinrich Malleson, looking at muscles in T-Rex and what their forces may have been like. And I was very conservative with my muscle forces for T-Rex back in my older papers. And with Allosaurus, I was a little more rigorous. So the forces and accelerations we have for T-Rex I've kind of published on are pretty they're at the minimum. So the more we learn about these animals, the cooler they get. So I'm going to shift gears a little bit and get into really try to highlight what some of my grad students and colleagues and collaborators have been doing, and what I've been doing most of my funding for the last since started up in 2015, and I gotten a lot of funding in the last 3 or 4 years or so to look at dinosaur growth, and so to look at the vasculature within dinosaur bone and look at the cells within dinosaur bone, or the spaces where cells might have been. We put the bones in front of a very pure X-ray source, and we've been doing this at the Canadian Light Source Synchrotron up in Saskatoon, Saskatchewan, Canada. And with Brenda Hart-Farah, she's kind of taken a lot of this and run with it. And we have a separate paper coming out that's going to hopefully have some of these results soon. And so what I'm doing with Brenna and with Holly Woodward-Ballard and with some help from Lindsay Zano is doing like 2-dimensional to 3-dimensional reconstructions. So we do 2D thin section slices, and then we do 3-dimensional reconstructions of those blocks that we have embedded in the bone in, so we can section them. And then looking at the bone on either side of that embedded block. So here's Brenna working on I think that's a Centrosaurus. Brenna can steer me wrong. Steer me correctly. That's either Centrosaurus or Myosaurus she's looking at right there. So just so you some of the things we can get out of here. So this is way back in 2015. This is actually pretty low resolution. And we're going to look at blood vessels within dinosaur bone. And all the little spots you're seeing, that is not noise. That is the impressions of where bone cells were. And since then, we've had vastly greater ability to resolve these cells at these bone cell spaces. So kind of stepping through the bone, any one of these could be a good histological slice. So kind of show you what's happening with sort of in a longitudinal section through the bone, how you might have maybe some connectivity and maybe some be able to sort of classify the bone. And here's something that Brenna did. So this is actually a bison bone. And so this is showing what things are like in 3D. And you have sort of large spaces between trabeculae towards the marrow cavity. You have larger vessels that, some connect up and some don't. And so this is a mature bison that we see here. So that's pretty cool for 3D. And we can explore within the bones. So this is a specimen we hope to publish on soon. And you can really get a physical feel for the structure and the size of the canals within these bones. So we're flying into the bone of this fairly small animal, and you can see how there are sort of larger larger vessels that are cutting through the bone, surrounded by smaller vessels that are building it. So the larger ones are cutting cones of remodeling canals. The smaller ones are vessels just building up the bone in all kinds of directions. So I'll show you that again because it's pretty cool. So imagine you're in the Millennium Falcon and you're flying into this this small dinosaur bone.
That's no moon.
There we go. So that's pretty great. Gavin King at the University of Saskatchewan, who's a student of David Cooper's, he made this video of some of our work. So that's kind of what we're doing for looking at growth in dinosaurs, both growth and activity levels. And Brandon's kind of figuring out the differences between those. But we're still kind of looking at locomotion and at feeding. And so here's my old student Zella Kassar, and she did this amazing reconstruction. This is life size on a poster of a Raptorex, of its muscles. And some of our recent work has been on sort of how agile dinosaurs are. And I urge everyone to seek out talks by Tom Holtz, who has basically gave him all of my slides, and he's been running with those. But what we're finding is that tyrannosaurs in particular had proportionally big leg muscles, and they had compact bodies from nose to tail. So there's a lot of variation within theropod dinosaurs, and the size of a given attachment doesn't dictate the size of the muscle, but you can still overall look for trends in how hard it was for dinosaurs to turn, and then how well they can turn with their muscles. And so this is a version of an image that Brian has in his background, where we did calculations on these animals. So I do things in a very abstract sort of physics sort of way, and then I'll use software, and I trust my methods because I know what's behind them. So then I'll sort of look into the methods that other people are using and make sure those are okay. So what we're seeing here, actually, Andre Rowe put together this Gorgosaurus over here, and kind of determining, how rapidly these animals might have been able to turn. So we have this is Sue over here. I think this is might be Raptorex, and then we have a Gorgosaurus there. You guys can see the pointer. And so with a large team of researchers, including Heinrich Malleson and Don Henderson, Don and I kind of check each other's work, and mostly Haley O'Brien. We looked at agility and different kinds of carnivorous dinosaurs, and so agility is kind of over on we're here on the y-axis, and we have log 10 of body mass on the x-axis, and tyrannosaurs. It's kind of hard to avoid that they were more agile than other carnivorous dinosaurs. So for given body mass, they had at least the muscle attachments and the rotational inertias to turn a lot faster than other carnivorous dinosaurs, that kind of the same size. Looking at some of these, say the forces of what happens if you're trying to maneuver. I had a student, Omid Darbani, who's was a student of colleague of mine, Dolores Vasquez San Roman, and we did some stress and strain analyses of the femur of a T-Rex. It turned out it could pretty much handle sort of low speed maneuvering without too much trouble, even at its large body size. Bill Sellers found out that if a T-Rex is trying to run too fast, its limb bones don't like it. But for low speed accelerations, it was doing pretty well. And this is for an adult T-Rex, so the juveniles were pretty scary. And so sort of going along with agility, as Brian Brian has brought up, we came out with a recent paper on Tyrannosaur feet and ankles, and here's Lara Suring, who's now an emergency medical technician in Calgary, Alberta. And Lara realized that we can look for microscopic traces of ligaments, ligament attachments in the bone of carnivorous dinosaurs. And Tony Russell and I had posited that ligaments would be present, but where they would be present in the metatarsal, say, of a Gorgosaurus, where they might be in a Coelophysis. And so Lara did scanning electron microscopy, and she and Mike Burns did fine scale histological sections. Danny Barta, a great colleague of mine here at OSU, he looked for ligament attachments in Coelophysis. And it turns out tyrannosaurs had a whole lot of ligament attachments down by their toes. So we're looking at the bones of the flat of the foot in these dinosaurs, the metatarsals. And their toe bones, individual toe bones, are kind of coming out from there. And tyrannosaurs had this weird sort of double wedge. So it looks like the central metatarsal looks like a wedge coming up in between the others. And that's both sort of in front view. And if you take a cross section through these, they have like a weird wedge system in there. And Tom Holtz did a lot of the really primary work on all of this. And what Lara was able to show for us is that tyrannosaurs really did have these big giant ligaments across huge, huge surfaces connecting these metatarsals down by the toes. Whereas something like Coelophysis here, even though its metatarsals are very closely pressed to each other, closely touching, do not have those correlates for ligaments to the extent that you see them in tyrannosaurs. They're basically, they're barely there. So that was kind of intriguing. So we really use Coelophysis as a good negative control. So we figured, okay, well, we're going to find a dinosaur. We're going to see where there might be these ligament traces, or see where there might not be these ligament traces. So if we're looking at a place where those ligaments were definitely not, then if we don't find those traces, then we're probably on the right track. If we do find those traces, we're probably doing something wrong. But it turns out Coelophysis did not have these attachment marks on its metatarsals. And so the way it works is like muscles attached to bone through tendons, and the tendons kind of pull on the bone from, so if this is a bone surface, here comes tendons are coming in. As the bone develops, the tendons ossify within the bone. And the fibers of collagen fibers in the bone within the metatarsal, say here, kind of wrap around and solidify around the ossifying fibers of those ligaments. And so we have pitting on surfaces that shows ligaments are there. We have direction of vascular canals that shows ligaments are there. We see these fibers within the bone. So I'm wiggling here. These are these fibers called Sharpie's fibers. We see those within the bone. And so our older ideas about potential for stronger feet in tyrannosaurs really bore fruit thanks to Lara's work. So finally, just some previews of future stuff. So here's Evan right here at Paul Sereno's lab at the University of Chicago. Here's Amanda Pettings with her poster on Innistransevia. And Evan and I and Amanda and I at SVP took some work that Amanda did and had her continue with all that to look again at Veranid lizards as sort of our extant, our living reality check. And we're actually introducing a new model or a new method of structural mechanics that's different from the traditional method in which it's called finite element analysis. And Evan has explained it, where you treat a solid as a bunch of interconnected springs. You push on one spring, it pushes on another, things deform, and you get strains, you get deformation of bone, and you back calculate stresses from those. And we're introducing a new method that doesn't require this internal mesh of interconnected springs. And Amanda found that we got pretty close with this method using the new method, pretty close results to the old method with really very high resolution traditional finite element models. So what's good about this method is it potentially speeds up the preparation time for these models and lets us rapidly test, basically rapidly hypothesize stress and strain from different bite forces in these animals, and potentially different sorts of material properties in their bones as well. So what we found, it's a bit of a spoiler, is that with the teeth in the middle of its tooth row here, the stresses from anterior to posterior in T-Rex actually went down for a little while. So it was biting really hard, and the teeth are getting closer to muscle forces, and the muscles are really pulling on the bone. But these big giant teeth here were on pretty much even stresses throughout the middle of this row. And they're imparting even maximum stresses to the whole skull. So we thought that's pretty intriguing. So T-Rex was able to bite pretty hard, pretty far out on its jaws, and maintain some safety for its skull. Like Evan found, and like Andre Rowe found for the mandibles of these dinosaurs, tyrannosaurs were biting really hard, and they had these big, as Ian Kost found, these big sort of solid skulls, weren't moving around very much. They had fused nasal bones along their snouts. The skulls were wide and tall with a lot of bone, and yet tyrannosaurs' bite forces were increasing really fast. And so they were actually afflicting their own skulls a little more than other carnivorous dinosaurs were. But the skulls were strong enough, and the bite forces were high enough to be effective. So lots of neat stuff still to come on dinosaur feeding. So I think I'll stop the share here, and we'll sort of come on back. And hang on, let me stop my slideshow here. That might have worked.
That was amazing. The chat is just replete with all kinds of questions. So I may work my way down just from FIFO status here, because there's some really interesting questions that'll take a few minutes to unpack. So first of all, amazing work. It is so cool for me. Yeah, I'm out here in Arizona. We're like on an island in a desert. So there's not a lot going on out here. None of the universities here have paleo, unless you consider paleoanthropology, and that was what I cut my undergrad teeth in. And it's about as vicious and violent of a realm. And no place for a smiley guy like me to hang out in. And to hear that you have a lab, you have these colleagues and all these folks out there, I'm just excited to just imagine the Friday evening hops and barley sessions that are just going on, and the ideas that are flying around. So kudos to you for building a wonderful venue.
A lot of that was Ann Weil and Kent Smith, who kind of got the paleo program started here. We have a really good group of people, including Danny Barta and Zach Kluckert, who's a paleontological anthropologist, and Holly Woodward Ballard, and Ian Brown, and with Jasmine Krogan. We have a whole group of great researchers here.
It's like you have an all-star football team hanging out in Oklahoma and thereabouts. So that's so cool.
Yeah, thanks.
My pleasure. All right, I'm going to go through and just go from the top. Let's see. Scanning. Everyone loves snacks. What's the Veranid lizard study at a high level? What are you looking to gain or learn from it?
Right. So Evan can chip in if he wants, but what we're really looking at is how Veranids use their neck to feed.
Yes.
Yeah, go for it, Evan.
Yeah, so we're mostly taking a look at, there haven't been as many studies that have taken a look at muscles muscles responsible for food procurement. So we're going to be taking a look at the jaws and neck muscles that would be responsible for it. And depending on what we may do for my PhD research, because I'm looking at theropods, we may do like some X-ray scanning and take a look at the actual muscles in action. And we can probably use like a comparative study, so take a look at other Asian water monitors and also Komodo dragons too, and probably other reptiles and birds too, for like a better comparison as well. And for me, I'm kind of interested in looking at head and neck or craniocircle feeding in theropods. So it's going to be more like, let's take a look at extant animals and do some extant comparisons and see what we can apply to extinct animals.
Well, thanks, Evan. As we filmed Komodo dragons at the Tulsa Zoo. It was pretty amazing experience. We're looking at Veranids to ground truth what we're doing with the extinct theropods. If we are able to make, say, a model of a Veranid neck moving, even just a couple of vertebrae moving relative to each other using our methods, that's a first stage in adding confidence to what we're doing with the extinct theropods. So it's what level of generalization versus specificity we can really use for a lot of our inferences. So it's really important to make sure the methods we're applying are not leading us astray. And so that's why I tend to take a very abstract theoretical approach to a lot of this, because I'm comfortable with my calculations of equations of motion and all that. And the physics side is okay. But what we need is, we need the raw muscles. We need the living animals to show us how specific the physics can get. So how well our simulation methods can really do. So we're always sort of starting big and generalized from large scale sort of principles of mechanics and of biology, and narrowing that down. And the sort of extant validation work that I've done with like how birds actually use their neck muscles and how Evan might do it with Veranids, that's but it's actually really great. It works in two directions. So what we learn from Veranids will inform the dinosaurs and vice versa. So when I was doing electromyography of chicken neck muscles, so we attach electrode to the surface of the skin of a chicken, because I don't like to hurt animals, so it was just as minimalistic as we can get. And we feed them mealworms. The chicken was using a particular muscle to roll its head from side to side, roll its head really fast. And it was pretty active then. It was also active when it was turning its head from side to side and when it was lifting its head a little bit. But that roll is something I had not considered. And you can then go back to like what we might have done with Tyrannosaurus or Allosaurus, and we can see are the attachments in T-Rex and Allosaurus, are they able to do that sort of rolling motion that Allosaurus, or excuse me, that chickens can and do. So we learn not just validation from the extant animals, we learn capabilities that we haven't imagined yet, or we haven't really touched on based on what we've inferred so far from the extinct ones. So animals do things that we would not expect, and they're here to teach us. So the Veranids, as we're kind of working in parallel with the Spinosaurus with Evan, T-Rex with me, Manabu Sakamoto is doing awesome work with dinosaur neck motions in the UK. Doing that in parallel is okay. So Andy Dannison, he absolutely did not want to do any modeling of arm motions until he was dead certain that a muscle was there. So he was going to go in, he was going to look for Sharpie's fibers, look for these muscle attachments, and he was absolutely not going to do the biomechanics. And so he was doing it right. So he was looking first at the modern stuff and then working his way up. And he realized that he could do both at once. So he can refine his modeling calculations based on what he's learning from attachments of muscles in extant animals. So I think that's sort of the direction I come at it from. We're sort of we're whistling happily in the twilight with our analyses and our research on extinct animals, unless we have this sort of vivid perspective, literally live perspective from modern animals.
It's just nice to see the validation as over the, you and I are similar ages career-wise. I think we've come up, the arm waving, you make an assertion and then you find something that kind of matches it downstream, because that's just the way people did it long ago. And now it's the engineering and the science and with the tech that's involved and the amount of computational power that exists and all of these new software packages that can do so much of the heavy lifting. It's that's why labs like yours and where you're at, Evan, just they make me smile. I look over there and go, wow, the next generation of paleontologists have it so much easier. And I won't even mention EndNote.
Yeah. Yeah.
Thank you.
The next question is the idea that Allosaurus's skull could resist a force 15 times greater than its bite still accurate?
I'm not sure about the exact figures there. So it may have been Emily Rayfield's initial findings. Some of that, the actual figure, we're not really sure of, or I'm not really sure of. And Emily Rayfield may have done some refined work since then. What we're doing now is Casey Holliday's lab with Caleb Sellers, Ian Cost, and John Fortner and their group. They're looking at soft tissue attachments as well. And we're not certain yet if the ligaments are helping a lot or they're really weak points. So something that Andre Rowe and I found, we put ligaments through the lower jaw bones of Jane, the juvenile T-Rex. And we actually found that stresses at the teeth went down. So the ligaments are able to take up a little bit of strain, and the stresses, the deformation near the teeth actually went down. And what that would mean is that the teeth had a little bit of headroom to bite harder. So you have a ligament running through the jaw of a dinosaur, and you'd think that that's going to make it weaker, less than 15 times as strong as the bite. But they have really, really important effects. And Casey Holliday's lab is doing really vital work on like where the mandibles, rami of the mandibles, sort of come together in the jaws of these dinosaurs. And so I'll answer the question in another way, like related to what Allosaurus was good at doing. So Allosaurus was very good at moving its head downwards into prey. And whether it's the sort of hatchet-headed hypotheses that Bob Bacher came up with, and they actually made sense from Emily Rayfield's finite element analyses or something, or just digging in and ripping back. The head was probably strong enough to handle those forces. And we're seeing really fascinating new work on the teeth of Allosaurus and how different kinds of theropods in the Morrison Formation had teeth that were maybe better or worse at cutting into bone. There was a paper that came out just this past week on that. And so Allosaurus may have fed on bone or may have cracked through bone in a different way than Tyrannosaurs did, with this sort of downward motion of its head. it turns out if a T-Rex dipped its head downwards, it would have really good leverage for that anyway. But having that sort of overhead, that sort of wiggle room, would have helped Allosaurus. 15 times, I don't know it, but there's certainly a good enough safety factor for it to be a very effective carnivore.
And along those lines, with mouth opening, I always see Allosaur, not always, I often see it with the hyper widened mouth. Have you looked at anything along those lines, or do you know of any along that topic?
Yeah, Stefan Lautenschlager did a pretty cool paper where he was looking at gape, so how wide theropods could open their mouths. And it looks like they could open them pretty wide. Just how far they can swing past a certain level, we're not quite certain. So Casey Hollidays pointed out that the wider you swing your mouth open, the less effective your jaw opening muscle becomes. And you end up just kind of squashing it and it kind of going limp. However, if you see a sort of physical model of just about any carnivorous dinosaur with its jaws opening to a certain level, like my friend Darren Molinaro made a sort of a jaw opening and closing model of T-Rex, a life-sized one. It's pretty terrifying. So sort of having Allosaurus with its jaws open, rushing and running into prey, probably not necessary. And opening really super wide, I don't really know about the range of motion there. But it would have been scary no matter what.
And speaking of scary, since they had big leg muscles in proportion to their legs and body, does that mean that tyrannosaurs were made for explosive movement?
That's such a good question. We don't really know enough about number one, about the moment arms that were going along with those muscles. That's going to dictate sort of how quickly you accelerate versus how quickly you can kind of move at a steady state. But having those big leg muscles, it's really, especially with young tyrannosaurs, it's sort of hard to get around the idea that they could probably accelerate pretty quickly. I suspect that Abelosaurs might have been even better, smaller muscles, but bigger moment arms. But another thing that goes along with that Alex Duchecki and his colleagues have really shown us is that having, at least having long legs helps you walk very efficiently, so cover ground very efficiently. You can do that with pretty light leg muscles. And so with like pretty big leg muscles in T-Rex and other tyrannosaurs, I tend to think they could accelerate pretty well up to fairly low speeds. So explosive movements, explosive for big, giant, slow-moving animals. I think that's probably the way to look at it in a relative manner.
And then does that tie into them being fast runners, fast walkers, slow runners? Where does it all end up as of today?
Yeah, that's a really great question. So what Alex's group found was that things like tyrannosaurs could walk really long distances, really energetically efficiently, exactly like humans. So, or exactly that sort of ability. So we do it in a very different way. We have big gluteus maximus muscle. It runs down to big sheet of tendon in our knees. We have really good springiness sort of with our upper legs. And whereas dinosaurs and other animals with longer legs have more sort of springiness lower down. So definitely younger theropods were probably running just fine. The bigger ones, it depends on your definition of running. So if you can launch yourself up a little bit into the air, so raise your center of mass a little bit, but not necessarily release your foot from the ground, that still counts as running. It's called Groucho running, after Groucho Marx, who had a really funny sort of walk. And John Hutchinson kind of brought this to light, that you can run without running, and getting both feet up off the ground seems really unlikely for some of these really big theropods, because as Bill Sellers found, if they're going too fast, they're probably overstressing their leg bones. And in Bill's paper, he referenced some of my work that showed you can obviate some of that if you have kind of stretching ligaments and tendons everywhere. But that goes back into sort of explosive moving versus fast running and everything. So I suspect that that it's kind of neat actually that Bill's work showed that like a big T-Rex was moving at about the lower bound of speed that John Hutchinson originally was calculating for an animal, for a tyrannosaur that size, quite a number of years ago. So that sort of convergence is really encouraging. It means we're learning about how the dinosaurs were awesome. Like, I don't care if T-Rex could run 50 miles an hour or 12. If it's running 12, that's scary. That's pretty cool.
Having been charged by a rhino in a
Oh, God.
I'm absolutely, yes, something 4 times the weight of the one that charged me, with teeth that intent to kill, as opposed to just, I got too close to its baby. Yeah.
Yeah.
Switching gears a bit, and I don't know, I'll be interested to hear your thought on this, and then we'll open it up for any live questions y'all have, because we're coming up at the top of the hour, and I want to be sensitive to the time. Question on binocular vision in tyrannosaurids. I know Lithranax and T-Rex had binocular vision, while Tarbosaurus probably did not. My question is, did Zhuchang Tyrannus, Daspletosaurus, and Gorgosaurus have binocular vision too? And was this the ancestral condition for Tyrannosaurids since Lithranax had it, or did it evolve multiple times independently?
Yeah, Lithranax is amazing. I'm really glad that animal's out there. It's kind of like it's a smaller analog to Tyrannosaurus Rex. It's really cool. So in terms of binocular vision involves the amount of overlap of visual fields. And even if your eyes are out to the side, you'll have a little bit of overlap of visual fields kind of far in front of you. And Kent Stevens talked about this on Paleoportal just a couple weeks ago. So Zhuchang Tyrannus, we don't have and I'm probably mispronouncing it, probably Zhuchang Tyrannus. Evan, how do you pronounce that?
It's Shuchung Tyrannus.
Shuchang Tyrannus, okay. So Shuchang Tyrannus, we don't have enough of its skull.
Yeah, we only have the maxilla and dentary, although if I recall from what Jingmei and maybe Dave Owen said, there's probably some like smaller scrap material too, but not much to go after.
Right, so Tarbosaurus had a narrower skull than T-Rex, especially in back. Daspletosaurus and Gorgosaurus also were a bit more narrow skulled. There's sort of a danger of relying on plausible reconstruction. So Greg Paul has a really cool reconstruction of Daspletosaurus, kind of looking vaguely at you. And Greg Paul's his stuff is very convincing. He's a great pioneer and sort of a biologically thorough dinosaur reconstruction. So I'll pass on Daspletosaurus. For T-Rex and animals in its environment, sort of Nanotyrannus style, young animals had a lot of overlap in visual fields. And again, there's not much of a way around it. So they had the potential for good stereoscopy. So being able to judge distances very well, for breaking camouflage. In terms of the neurological capability for that, that's a little harder to test directly. So you'd want to look at animals today with given overlaps of visual fields and see how good they are at sort of judging distances and things like that. And so whether it's archaic for tyrannosaurs, whether it's plesiomorphic, which was the original condition, having that sort of vision, at what level it is, whether it's like T-Rex and Tarbosaurus and Lithranax and its relatives, or whether Lithranax and T-Rex kind of evolved this independently, I'm not sure we have the evidence to tell, but some degree of overlap was certainly there. Probably less so than things like troodonids or or T-Rex or Lithrinax.
Well, we are at the top of the hour, so if anyone has any questions, jump in now.
What key anatomical innovations allowed tyrannosaurs to outcompete other large predators from the early Cretaceous?
So that's a good question. Tyrannosaurs had anatomical advantages. They had adaptations that made them pretty good at what they did. So you have the arctometatarsus. So you have this wedge and buttress foot structure. You had expansion of jaw muscles that sort of happened through tyrannosaur evolution that Evan has really had shown us, and Andre. Like Tyrannosaurus rex itself, it's almost like a chameleon's worth of weird, cool adaptations. Not quite. Chameleons take the prize, but you have fused nasals, you have bone that's going into the infratemporal fenestra, you have everything sort of locked together really well. You had diamond-shaped vomers that were attaching to maxillae, so the bones of the roof of the mouth that met in the middle for sort of a really powerful or strong torsion tube. You had stereoscopic vision. You had these big wide teeth. You had the ability to grow really fast. You had the largest leg muscles for its body size at any age, and compared with most animals. So that's all great. But despite the picture I showed kind of the beginning of my talk, you didn't really have T-Rex squaring off with Allosaurus. You didn't have a rumble between Abelosaurs and Tyrannosaurs. It'd be nice if they did overlap. And you also had the potential for niche partitioning or sort of eating different things. I'd say the advantage that Tyrannosaurs had was the capability for that kind of rapid and continued growth. So, and I'd probably say just really big leg muscles by the retention of a deep tail, and really expanded hips. So those are advantages, rapid continuous growth and big leg muscles that dromaeosaurs did not have. So dromaeosaurs, larger dromaeosaurs, like Chelobatar and Utah raptor, and some pretty cool stuff maybe happening that Kyle Atkins-Weltman is working on. They couldn't get that big. And I actually saw something in the chat about niche partitioning that Kat Schroeder has been working on. So you had tyrannosaurs as maybe competitors to dromaeosaurs at different life stages. And Kat Schroeder has done this amazing work showing that and I actually don't want to give away her stuff, but she's looked at tooth wear in tyrannosaurs that is showing what the babies are doing, what the teenagers doing, and what the adults were doing. And that shows what they're doing relative to their potential competitors.
I think I'll reach out to Kat and have her a guest next year.
Yeah, she's done some mind-blowingly awesome work. It's kind of like Brenna Hart-Farah is doing with 3D histology. Kat Schroeder is doing with sort of bring a whole bunch of evidence together for the sort of ecosystem structure in dinosaurs.
Awesome.
Could theropods have hunted using intelligent strategies?
When food is involved, animals are a lot smarter than we give them credit for. So I found that what we sometimes see is as long as crocodilians are conserving energy, they can be pretty smart. So crocodilians tend to tire themselves out pretty quickly. So that means, extinct dinosaurs may have had the bandwidth, sort of the metabolic bandwidth to behave, maybe appear to be a little more intelligent more of the time. So it's why, like what you've done with the water monitors and what we see with crocodilians, why it's so important to look at modern reptiles, including birds. A good example would be ankylosaurs and ceratopsians, who have pretty small brains in absolute terms and for their body size. And I kind of like to know what they would probably surprise us. They would probably do things a little more smarter than we might think. Another way to look at it is, so the overall brain size and the size of the parts of the brain that Ashley Morehart has done a lot of work on, give us a sort of idea of relatively how much an animal is using different parts of its brain. So pterosaurs have the largest cerebellum and the largest sort of balance organ, the flocculus coming off the cerebellum, relative to brain size of any animal. And tyrannosaurs and dromaeosaurs have big olfactory bulbs. So how the animals are using their intelligence, you can sort of get some idea, like maybe tyrannosaurs were doing something clever with smell, and pterosaurs were doing cool acrobatics. Do you have a follow-up or an intercalary question before I continue?
Why did large theropod carnivores evolve elaborate crests and display features? And how did they offset the costs of such features?
The benefits were greater than the costs. If an Allosaurus it's a cool, one of the coolest looking dinosaurs. Cool horns, lacrimal horns above its eyes, ridges on its snout. If that made it, slightly more conspicuous or scary to an herbivore, or if it had bright color patterns on those, it would have been attractive to another Allosaurus. And that's what it comes down to. So the benefits in this case of being attractive enough to procure a mate, you kind of have to do that to keep all of these adaptations going anyway. So those are the advantages. And another advantage that tyrannosaurs were apparently really bad at was avoiding conflict. If you have elaborate signals, and you could potentially avoid biting each other's faces open. And Tyrannosaur did that anyway because they weren't very bright. But so the benefits, I'd say the benefits outweigh the costs in some way.
If so, why haven't modern animals evolved similarly elaborate features?
That's such a great question. Yeah, it's such a good question. I would kind of defer to, well, number one, because reptiles see well into ultraviolet, they're probably more, and they are more intriguingly colored than we give them credit for, than we can perceive. Even the Komodo dragons that we worked out at the Tulsa Zoo, just gorgeous patterns. They look from a distance like kind of gray or whitish. We're lucky as primates, so we can see the colors we can. But reptiles with fourth opsin water droplets or oil droplets in front of the retina, or sorry, I should say in front of the light gathering cells, they're seeing things we can't. And I wish I could experience it, but can't really do so.
Why was agility measured as iliac area divided by the y-axis moment of inertia? And what makes that ratio a good proxy for agility?
So the y-axis is straight up and down. So that's the axis of yaw, the axis of turning from side to side. So that's why we chose that. And we chose it around, you have to do it around the center of mass, or sort of collective center of mass. And an animal can still turn while it's unstable. But we did it with sort of 1 foot off the ground and the animal swinging around its this collective center of mass of the 1 foot, or the one leg, and the body pivoting. And we did it with both legs planted on the ground. And another way to look at agility, which is actually really intriguing, being able to strike downwards. So that would be about a horizontal axis. And so that would be in pitch. And something we really never think about is roll. And so being away on one side of an animal and rolling your body over to the other side to sort of help yourself out with turning and turning down. I have all of those values, and you just have to look at the muscles that are involved in all of those. So we do have to narrow down we're talking about generalizations versus specificity, and we have to narrow down to specific muscles to look at real turning ability in any of these cases. Kyle Atkins-Weltman has done it for a big adult tyrannosaur. John Hutchinson did it for a tyrannosaur as well. Something related to agility, and a big, slow, clumsy animal can appear to be turning slowly, and its angular acceleration will be okay, but the tangential acceleration, the sort of straight line acceleration at the jaws, can be pretty darn big. And what Kyle calculated something pretty terrifying for an adult T-Rex. So stay tuned for more about agility, about all those axes.
How does meshless finite element analysis work on skulls compared to traditional mesh-based finite element analysis?
I haven't looked into the math enough. So the way I would do it, you can determine stress in any cross-section by a summation of moments anywhere in a cross-section. And you don't necessarily have to have springs pushing on each other for that. So I actually have to go to the company with that. So it's a sort of the way they look at it. A whole skull is an element. The whole skull is deforming in a certain way, or an individual part is deforming in a certain way. So another thing they do that's really cool is you can have an assembly of bones, and it will connect those up for you. They really like to use welds, and we have to work with them to put in other properties. So I've been working myself on just spring constants, trying to map those to sort of ligament and tendon properties. So I'll find out, and we're going to be writing this up in the next little while. So it's the math might be beyond me. So I'll let you know.
Where do you stand on the controversial Nanotyrannus debate? And part two, in the Maastrichtian North America, could it have been home to multiple species of large-bodied tyrannosaurs, niche partitioning with one another?
So where I stand with that, I stand well on the fence. The facts are that the smaller teenage sort of tyrannosaurs that we have were still growing and show a lot of juvenile characteristics. Mm-hmm. So it requires a little bit of special pleading to say that, oh, they were at the end of their life anyway. They they just grew to a certain age and stopped, or they looked like they were still growing and they weren't. And some of the work that on the ontology of biomechanics that like Evan's been working on, Andre's been working on, those sort of tell us what the animals were doing, whether they were Nanotyrannus or Tyrannosaurus or something like that. There's a lot of good, weird specimens out there. And I think Nick Longrich and colleagues sent out a preprint recently, sort of cataloging everything that might be different than T-Rex, that is small and might be a legitimate taxon. So that's great. There are animals out there sort of on the gray, in the sort of gray zone of specimen legitimacy, put it that way, whether they're accessioned or not, that so there's some diversity of these sort of mid-sized tyrannosaurs in North America. So, well, Jane has long, spindly legs and can easily grow Jane into an adult T-Rex. But there are some tyrannosaurs out there that might have thicker teeth than Jane does. And what's happening with individual variation and all that is unclear. So even Holly Woodward Ballard, who published a big paper on it all, she's agnostic. Phil Curry, Tom Holtz, Larry Whitmer, anyone smoking gun that you have, like you say, oh, pneumaticity is showing this animal is different from an adult T-Rex. Well, animals change during growth. So we don't have a good enough handle on it to be quite sure. So there are certainly a greater variety of tyrannosaurs in Asia than in North America. So there's Alioramines that Evan's working on, and Kyle in our group. And it's plausible that there are other kinds of tyrannosaurs or other kinds of large theropods in North America when, say, T-Rex or Daspletosaurus and Albertosaurus and Gorgosaurus were around. We don't really have, we need more fossils.
And just to add to that part about with Jane, I measured the adductor chamber area for most of the juvenile tyrannosaurs, and they are monstrously wide compared to others of their size, skinny tyrannosaurs. So it's possible, and they kind of match that with some of the adults too. So like Pseudonation Sierra with Tarbosaurus, Jane just for a medium-sized tyrannosaur just had a ridiculously wide adductor chamber and very high jaw muscle force too.
Yeah, like Jane was biting like a junior T-Rex. It wasn't biting like Teratophonius. Teratophonius' skull is exactly the same length. Jane was just crushing it. Teratophonius is super cool, but yeah.
I grew up in the Morrison, the BYU collections, the Stokesosaurus, Marshosaurus.
Yeah.
Tandicalagrius, Salurus. You've got all these theropods in one quarry. When you start off with the most diverse quarry, everything else seems barren in comparison. And when I move in and I travel, I'm like Gandalf the Grey. I visit so many museums. We've 72 this year. And I see private collections. And I see things like SWAU, Southwestern Adventist University's strange little critter. But Dave Berman's got that he's going to be publishing on soon. And that bizarreness. It strikes me as peculiar that one species would occupy every single niche exclusive to any other animals coexisting from a logical standpoint. But I'm excited to see how this all turns out, what the dueling dinosaurs bring to the fray. And I agnostic, I like that term. Science is going to say what it's going to say, but I had a professor in my undergrad say the specimen numbers stay the same. Everything else, you're on your own. It's good luck. So it's nice to hear that you're more of the, let's see what comes out. There's a ontogeny is so critical, variation, but it seems to me that if it is any other theropod but T-Rex, that would have been split 50 years ago, 30 years ago into multiple taxa. 5027 is so different than some of the other specimens of T-Rex. And I'm a sauropod tail guy, and I can at least externally look and go, man, that's a huge range of variation, because then I roll it back to the Morrison. Well, should we really be splitting all of these, or are we looking at tremendous ranges of variation there too? And then BiDove, you talk with Napoli and his new software. I told him after his talk, I said, so you've just given everyone a license to print species.
Well, I'll tell you right now, not more than 20 to 20 feet from me. I have to think in metric, about 7 meters from me, there's a room full of people, a room full of our donors to our med school. And every one of them has a feature that would be generically diagnostic if we were to discover it as a soft tissue fossil. There is so much variation. There's so much variation through ontogeny that it's okay not to know. It's okay to realize that if Jane turns out to be a nanotyrannus, then, well, that's great. That means we can say cool things about Jane and these larger T-Rex type critters running around. It's okay if we have this really good progression, this really good pattern of growth. We learn something new and cool, and we want to know. It's best to want to know. Try to avoid being invested in whether you're right or not.
That's where, so well said. I look at, you look at the range of variation of animals we look at today, and birds. I mean, I'm a hobby birder. Every year there's puts and takes. There's 30 new species gained and 70 lost, and they're moving around. And these are animals that we can go take their blood, their DNA, we can listen to their songs. It's just incredible. But I find that there's a meta take, which is anatomists. You mentioned Larry yourself. The anatomists tend to be the most, hey, just kind of, who knows? We're going to let time tell. They're
really interesting.
The phylogeneticists, the cladists, they're arguing over the character nodes. And it's almost like what genre you study determines your level of hot-bloodedness over is Nanotyrannus real or not. I should write this up in a fun little blog that and name names, because everyone will self-recognize. Like, yeah, that's me, totally.
Yeah, you can quote me on anything, just whatever you want to do.
Got it.
Can insight into tyrannosaur growth help resolve whether Raptor Rex and Nanotyrannus are distinct tyrannosaur species or simply juvenile T-Rex and Tarbosaurus?
Wow.
If you want, Eric, I can actually help out with the Raptor X part.
Sure.
Yeah, so if I recall, the Raptor X specimen is now being sent back to Mongolia. Paul has been talking with Chinzarig regarding its specimen, and he thinks the Raptor X is probably a juvenile Tarbosaurus. And when we took a look at both the Tarbosaurus that I believe Taka described and even Raptor X, there were some slight differences in the snout morphology. The baby Tarbo was more narrow snouted and Raptorix was more rounded snouted, but this could also lead into taphonomy and also how the original discoverers had prepared it too. They probably would have just sculpted it just to make it look nicer. I'm not sure how much of Raptorix is actually, well, genuine. Some of it could also be artificial, sculpted just to say like it's distinct though, but it can also lead into preservation, taphonomy, and also variation though.
So for Tyrannosaur growth overall in these specimens in particular, they were not fully grown, and they were probably young versions of something, whether they grew for another 2 years and just to the size of a horse, or whether they grew into Shuchung Tyrannus or Tarbosaurus, we're not really sure. So those particular specimens, that's a little unclear.
Can insight into Tyrannosaur growth help explain the apparent lack of medium-sized predators found in the Mesozoic?
I think you need Kat Schroeder on Paleoportal.
I just typed your name. I'm saying you sent me.
Good. Yeah, Tom Holtz has been looking at this for a few decades, and Kat came in and they sort of published almost simultaneously on the same issue. That there is a really big real gap between obvious adults of small predators and giant predators in the Campanian and Maastrichtian in North America. That gap is big no matter what. And dinosaurs had to grow up. And so when they were toddlers, when they were pre-teens, teenagers, when they were like, T-Rex undergoing its horrifying growth spurt, between 15 and 20 or whatever, they were doing something at all of those ages. And we talked earlier about advantages that Tyrannosaurus may have had. They could keep growing and Dromaeosaurs couldn't. So they were able to fill those niches. So imagine that we had Tyrannosaurs in Africa today. You would have what you would consider kind of medium-sized predators with lions and tigers, or excuse me, lions, sorry, I should say lions and hyenas and leopards and cheetahs. And then you'd still have a huge gap. You'd have, a huge gap in body mass. And so Tyrannosaur growth enabled things that Evan and others are finding, this niche partitioning. And the dinosaur nerd in me is just saying, Tyrannosaurus was good at whatever it did at every age. It was really, really good. And so that is a possibility. However, like we're saying earlier, we didn't have Tyrannosaurs out competing other large predators. They're really the only large predators in their environments. So their growth is giving us the pattern. It's showing you can have these intermediate sizes in certain taxa, so certain groups of animals, in tyrannosaurs, in allosaurids, velosaurs, and there weren't sort of medium-sized predators around that would fill in those gaps. So it may have been an issue with dromaeosaurs being really good at staying fairly small, rather than them somehow being really bad at being medium-sized predators.
Population densities between growth stages, how many subadults in a territory per fully skeletally mature, it gets complex quick.
Yeah, absolutely.
I love it. Well, thank you so much. This is for overtime. This has been an amazing experience. We'd love to have you back next year if you're willing to come back and share other exciting finds. You've given us a list of other people to go track down and invite.
I'm happy with sticking around till about 3 if you guys want to. I have a medical student who's making a 3D model of her own eye and her own visual system, and so I'm going to have to jump onto another Zoom call at 3. She's working on my computer through Zoom, which we actually haven't found works really well.
That is so great. I need to chat with you. There's a few post things just to go over with at the end. So but if anyone has any more questions, Dr. Snively's willing to field them. So in the chat, if I missed any, let me know, repost them. Otherwise, I have questions for you for 2024. What can we expect coming out from you directly in 2024? Or are you more maestroing people and you're now the conductor and your research takes a back seat?
Yeah, that's kind of the way it is. What I'll probably be doing is continuing. Evan and I have some cool stuff coming out, and we'll be doing a lot of collaborative work, continuing with the Tyrannosaur stuff. Brenna hopefully will be coming out with some of her work on 3D synchrotron histology. I'd like to get a good working head neck model of T-Rex going. I'll be working with, in part with Reina DeVries, who's a colleague of Evan's. She's a sort of a computer graphics wizard, Blender wizard, some of that. Working with Kyle on a lot of stuff. So what you can expect from me is probably an NSF grant proposal that we're trying to get together so we can do some of these things. With Callum Ross, who's Evan's committee chair,
wow.
Larry Whitmer and Casey Holliday.
I hung out with Callum for a month or a couple of weeks in South Africa in '97. It's funny to hear his name come back up.
Yeah, and I think this new meshless method, try and get that out there. So that's all pretty cool. Yeah, my priority is T-Rex neck motions, and so that's what we hope to do. And
Spinosaurus.
That's well, that's for you, Evan. I'm sticking with T-Rex. And yeah, but Spinosaurus is Evan's going to show what Spinosaurus is doing.
Yeah.
So other things like probably stuff coming out of our horse work, and probably stuff coming out more on the human anatomy side. Yeah, my student Kaylin Ray did an MRI-based model of her entire lower limb, and we're going to see if we can get Kaylin running virtually. So that's something we're trying in parallel with the horse and the dinosaur stuff.
The scary thing with that is I could see it going to personal trainers to say, you could go faster. Look, if you drop a few pounds and strengthen your muscle here, you can add an extra mile per hour. Forget this and go into weight training.
We're looking at a gait modification for female athletes in particular, because I have a great relationship with my old job with I had a lot of mentees on the track team, and so the women's track team would invite me to their meets out every year, and we have a lot of models, subject-specific models of their bones, sort of to look at stresses. Yeah, so it should be useful for athletic training, we hope, for both humans and horses.
Oh, I can tell you, way back when I was working with Kent Stevens in '95 on a program called Dinomorph and its predecessor, or actually its successor, and we got approached by a horse club that wanted us to model horse skeletons for whatever, and they offered us an obscene amount of money, which in hindsight we should have taken, but we were convinced that academic purity was the way to go at the time. I've subsequently revised those statutes, but in light of what ended up transpiring. But yeah, horses, there's so much information and so much money and grants and places you could probably go get.
That's what we're hoping. We're actually hoping for Department of Defense grants.
There's another question that popped up in the chat. Is the idea of juvenile Deinonychus being capable of flight still considered reliable? And I'm not familiar with Deinonychus ever flying, so that one caught me by surprise.
Certainly Microraptorines, so the smaller dromaeosaurs, were capable of, if not powered flight, at least really good four-winged gliding. And there are still Microraptorines like well into the very latest of the Cretaceous. And so you can imagine these four-winged critters flitting around in the trees. Baby Deinonychus, I'm not so sure. I think it's their forelimbs are already reduced enough. I think it'd be kind of difficult for them. It'd be great. Like we know they had quill knobs on their forelimbs, or on their forearms. So they certainly had strong feathers there. And Velociraptor had them. Some really big, much bigger animals had quill knobs, and so that'd be really cool to have a baby Deinonychus if it's feathered out enough. Climbing trees and maybe trying a little bit of gliding or maneuvering.
Awesome. Thank you all kindly. Good luck. Good hunting. Fly be free. We'll see you all in 2 weeks.
Yeah. See everybody.
Adios.
Dr. Brian Curtice is a dinosaur paleontologist best known for his research on sauropods, the long-necked giants of the dinosaur world.
This animal is near and dear to my heart. This will probably be the name-bearing specimen for our new species of Diplodocus. And I dug this out. I'm Not even humble bragging, I'm bragging. This took a long time to get out of the ground.
He has collaborated with scores of the world's leading paleontologists and has worked in hundreds of natural history, science, and dinosaur museums around the world.